Okay, today we are starting optimization. So last few lectures, it was mostly descriptive. I tried to tell you basics of neural nets, and then we had industry speakers. So now you'll go back to the flavor of early on in the semester. We will do some exercises on Canvas. And after some point, after optimization is finished, maybe 1 or 2 lectures in randomized algorithms, then we will have our second take-home midterm. So it's going to be more like the beginning. Do some exercises, get things going. There will be a small flavor shift, that's what I'm trying to say. Now, it's not a shift, it's going back to what we were doing at the beginning. And after optimization is finished, it's going to be a lot of different algorithms. Optimization is the part where we would see some technicality, and it is, I think, necessary technicality. So, okay, let me start by very basic geometry. So this, people can debate what's the best perspective to take on optimization. You got stuck with me, so I like geometric perspective, so you will see a little bit of geometric introduction. You would see some optimization books, there would be no geometry whatsoever, but I think it gets harder to follow a whole bunch of symbols one after another. When I see 2 pages of equations, it's much harder for me than seeing a picture. Okay. So I personally prefer, if I can see it geometrically, I have a better intuition. So I'll try to introduce you geometry. Okay. And optimization is what you do all the time when you train something. So you start your neural net from some parameters. What does that mean? Think about all that parameters like a vector. Let's say if you had a small neural net back in the day with 100 parameters, it's like a vector with 100 entries in it. And all we are doing, we are trying to find the best vector with 100 entries in it. You keep traveling through the space and you try to find the best one up to your criterion. And when you're convinced you found the best one, you freeze, you release your neural net. So, almost everything you do in data science and machine learning is an optimization scheme under the hood. So it's good to know the basics of the story so you can, if you need to tweak what you're using, then you would be capable. Otherwise, you take a package. If you're doing, say, very simple machine learning, scikit-learn. If you're doing more complicated, your TensorFlow, PyTorch, whatnot. And then there will be always an optimizer to be picked. And you just pick the default. Right? But quite often, what you want to do does not fit with the optimizing algorithm. That is the default. And if you have not seen the basics, it's hard for you to guess, okay, which algorithm should I pick as the optimizer? And then what should be my objective function if you're also changing the objective function? So hopefully, next couple of weeks will give you that background. So later on, we can tweak optimization algorithms or have an idea why this thing did not converge, when you run it. Right? All right, let's get going. So here you see 2 surfaces. This is like first sheet, I called it H1. Second sheet, I called it H2. And H1 intersection H2 is this curve. And suppose we are trying to optimize some objective function in this curve. So why do you see geometric objects? So usually optimization is subject to something, right? So you want to say, well, what got optimization on the map was mostly, in a way, linear programming. Linear programming was in Cold War era, more or less, or maybe earlier. So the issue they were dealing with was like resource allocation problem. You have a whole bunch of logistics. Where are you going to put your money and your logistics? You want to optimize some objective function, and you have constraints. Certain numbers cannot be bigger than something and cannot be less than something. Okay. And then the algorithm invented back in the day due to Danzig called simplex method. Still, we use a variation of it to this day. It was so effective. We have a different way of doing the same thing, which I'll not tell you in this course. Is something called interior point algorithm, but more or less that idea still serves at scale. Okay? And unfortunately, a lot of people with degrees in computer science graduate without even hearing basic optimization. So hopefully we'll do some of it in the next few weeks. You will have an idea. There was a survey there. So there are optimizing packages. So IBM used to have something called Simplex. They now discontinued it, and it's open source forked. It should be in GitHub somewhere. There's another big one called Groby, G-U-R-O-B-I. You have access through your UTSA accounts. And Groby made a survey with data scientists a couple of years ago, asking what is optimization or what is mathematical optimization as a problem, and what are standard algorithms, and then what are the tools you would use. And the output is like 70% wrong answers. So data scientists don't know optimization. They don't know they don't know. So that was the end result of the survey. And I can kind of attest to this personally. I have a whole bunch of friends who became data scientists, and they keep asking me very basic optimization questions. And I usually tell them, go to Google OR tools, which is open source. You can just pip install, and you just put your problem. It's called, say, job scheduling problem in operations research language or optimization language. It will solve it for you. Okay, you don't need to do transformers for job scheduling. So okay, hopefully you'll have a little bit more background to do that kind of stuff. So basically, these surfaces represent the constraints you have to pick, and suppose it happens to be a curve. So to get going, I need to tell you some very fundamental basic geometry. So let's say for the moment your surfaces are defined by some equations. It could be linear, nonlinear. I just made up an example. Let's say this is the constraints you have to obey for some reason, okay? And then after you have the constraints, you have an objective in mind, and you want to maximize or minimize depending on how you set it up. If the objective is a cost, you minimize. If it is gain, reward, you maximize. Okay. Then the first thing we need to think about is like, what kind of moves on this geometric space will change your objective? What kind of moves will do nothing? So let's say I'm moving in a direction. It's changing nothing for my objective. That's a waste of your resources. Don't do that. Right? So you need to have an idea of like which direction is reasonable to go. Then among those, you'll try to pick the best direction to change, to perturb your current situation. Okay, so the notion for that requires this thing called tangent space. But before that, let me draw a little picture. Suppose when we see something complicated, like a surface, we try to think about it through curves. Let's say there's the curve C that lives in the surface H1. Say this is my curve C, okay? And you can think about a curve as like a map that goes from real numbers. C, you can think about it, that goes from real numbers on top of this surface H1, okay? So you give it a number. So C, say 5 is a point here. C3 is another point you see. You plug in all the points, you get the curve, suppose, okay? So what would be if you take the derivative of this curve equation, if curve is C, what would be C derivative T? It should be something like velocity, the speed you're going on the curve, right? Geometrically, it will look like this, like a vector attached on that point to that curve, okay? And since curve is living on top of the surface, the vector is also like being attached to that surface, okay? This type of vectors, we call them tangent vectors. They are created by derivatives of a curve living on the surface, okay? And tangent vectors will do nothing, okay? So you shouldn't go in the tangent vector direction, maybe. Let's think about it, okay? So let's go slow before I get to a conclusion. So more mathematically, let's say if my surface was living in some n dimensions, I have a curve going from real numbers to Rn. And if the equation was H1, I plug in my curve inside, I always get a 0, which means the curve is living on the surface, right? That's what it means. The surface was defined by plugging your numbers to this equation, you should get a 0 out, okay? Now let's try to make this easier for myself. I put the curve in and I get out a number. So let's call the whole thing a different function. T gives you something on the curve, then the curve gets plugged into the equation and you get a number out. Let's call this a function that's now like a just one variable function. And I would like this thing to be always 0, meaning that the curve remains on the surface. If this thing is always 0, actually, then it's just something trivial. It changes, no change at all, and the derivative should be 0 as well, okay? So what would that mean, like in terms of this tangent vector we were talking about? So let's go try to roll back and go slowly. So what I said is like, this was my curve, C, right? C was going from real numbers on top of the surface. And the surface was defined by an equation, H1. So I'm hoping for every single new number I'll plug in, H1 CT is 0. All right. And now, if this is the case, then I called it a function now G1 something, right? G1 T. Now I want to think about the derivative of this function. And since this function is not changing at all, the derivative should be 0. But how do I see this in terms of these tangent vectors I was drawing? Don't forget, this is given by the derivative of your curve. How do I relate this very simple reasoning back to the geometry I was saying? Okay, that's the next thing we'll think about, and that's what's gonna tell us this tangent directions. All right. Okay, very good. And then the way you go about it, let's go back to what we know slowly. We talked about these directional derivatives. If I'm trying to take the derivative of my function h, defining that surface on a direction, v, this was like take the gradient, take inner product with that v. This is something we have done some time ago, right? When we were doing this vector calculus, back propagation, whatnot. So this was the definition of a directional derivative for a multivariate function. Take the gradient vector, multiply it with the direction you like. That's the directional derivative. That's something I know. What else I know? Hopefully you have seen Taylor expansion in some point at some course. If not, I'll remind you now, not a problem. Taylor expansion gets so much mathematics and algorithms and economics going that it is amazing. That's this thing from so long ago is so useful. What is it? You have a function that you deal with, and it's hard to handle the function. It's very complicated. So you try to come up with some approximations to it. How do you come up with an approximation? If you care to approximate that function around a particular value x naught, you evaluate it at x naught. Okay, at least you should be able to evaluate your function at a particular value. Okay. If you're trying to say optimize, if you don't know what's the value of your objective when you just check, it's impossible for you to optimize. So you should be able to do this at least. Then what's next? Hopefully you can compute the first derivative. Then you multiply it with the difference from your target, x naught, to wherever your x is right now. So this looks like this directional derivative, as you see. Actually, what you're doing, you're evaluating, then you're going one directional derivative step from x naught to the direction x you want to go. And then you can cut it here. That's going to be an approximation. If you want to be more precise, you also add the second order term, which means take the second derivative this time, put your directional vector left and right. Second derivative is going to be a matrix. You have to multiply it, left and right twice, so you get a number out. And that's our approximation, okay? And everything you're going to see in next few lectures, almost everything is going to be based on this idea, okay? We are going to design optimization algorithms using this guy, or using them both, or trying to see something that is close to this and easier to compute. If you're only using this, it's called the first order algorithm because it's only using the first derivative, right? If you're also using the second one, it's called the second order algorithm. The gold standard of second order algorithms is again due to a very old guy called Newton. It's called Newton's algorithm, right? And then Newton's algorithm is very expensive. First order algorithms does not always converge. There are also things in between, like say first order, second order, 1.5 order. 1.5 is called quasi-Newton. We will touch base along the way. And some of those quasi-Newton stuff is implemented in all the packages that we use. So you will see which one is which. You can pick up to your taste. Okay, so Taylor, let's get back to our discussion. So now, this is Taylor for my H. Let's do the Taylor for my curve. I'm at a point T. Let me just push it tiny bit. Do the Taylor. Okay. Now what's going on is like, if I put this or that inside my H1, the answer should always be 0. I plug in my curve inside that H1, always 0. So this should give you 0, that should give you 0. You know, how that's gonna work. That means the difference is essentially doing nothing when you put it inside your H equation, okay? And the difference is literally the tangent vector that we were talking about, okay? So all in all, what we are doing is actually, when you take the derivative of the whole thing, you're essentially taking directional derivative of your function, complicated one, in the direction of that speed vector. And this should change nothing, since whenever I plug in my curve inside my equation, I always get 0. All directional derivatives in that tangent directions, the velocity vector directions, does nothing. Okay. So that's a very important thing to realize in optimization. So that's called tangent space. Okay. For now, it might look abstract. We will get to a use of it soon. Use will be almost algorithmic algorithms probably today. Hopefully, I'll do gradient descent, and starting end of this lecture, we'll do more and more algorithms. So to be more precise, what does it mean for this directional derivative to be 0? We also have a way to write directional derivatives with the gradient vectors, right? So what was the gradient vector way? The same thing. Let me write it. So I expect this to be 0 all the time. And let me write that with the gradient way. That means I expect this thing to be 0. In other words, whenever I take the gradient, it's got to be orthogonal to my velocity vector. Okay. So all these tangent vectors are the orthogonal directions to your gradient. Gradient is like a normal vector. You know, the way to imagine this is as follows. You take the gradient vector of your function at that particular point, whatever that point was. And then you look at the things that are orthogonal to it. When you think about all those things, there will be all these tangent vectors coming from different curves. You know, okay. So this curve gave me one of those vectors. If you think about all the curves going through here, they'll give you all the vectors that are orthogonal to this guy. The punchline is this the direction given by the gradient determines all the directions that does nothing for you in the change. Yes. Sorry, this is like. Very good question. So because the definition of this guy is H1 x 0. And this x is a multivariate vector. And I'm looking at the case when this x is given by the curve. So as soon as I put H1, anything on the curve, the output is 0. So if you're traveling through the curve, you always keep getting 0. Okay? So it's very, I understand it sounds very weird. Yeah, that's why I'm doing this exercise, to get you guys used to this type of things. Somehow people either don't explain or assume everybody knows this. I don't know why. Okay. So what's going on is this, Adam. So let me draw the pictures from the get-go. So this is my curve. It lives entirely on the surface. And that means anything from the curve, when I plug it into the equation that gives the surface, it's going to be 0. That means traveling through the curve does not change anything at all for this function. So this also means intuitively, like if you perturb in the tangent direction to that curve, you shouldn't expect any change from your function. Because this tangent direction is like an infinitesimal version of the curve. Curve is a continuous thing. If you look at it locally, like this derivative idea, it looks like that tangent vector. Curve is like a flow. The vectors are like giving you the directions where that flow is going, right? So if I go in that direction, I should expect no change because curve is not changing anything. And what would that mean more precisely? It means take the gradient of that function, h. It's going to be always orthogonal to those directions. Yeah. 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 And that means in equation way, what I just wrote here. Take the gradient vector, take one of those directions, product them, you will always get a 0. Okay. Okay. Why does it relate to optimization? I'm getting there soon. So, so far, this is my surface, this is my tangent space, everything that is orthogonal to my gradient stuff. And if you have two surfaces intersecting, the tangent space becomes stuff that is orthogonal to both of their gradients. Okay. So I had one sheet, I had another sheet. Now, if I want to talk about what would be the tangents if I'm only caring about the stuff on this intersection, like what are those vectors right here? Okay. Those vectors are orthogonal to both directions, both to this and that. Right? So that's their common tangent space. Okay, very good. And now, what? So now, what is the common tangent space? Let me rewrite what is here. It is everybody that is orthogonal to both of these gradients, right? So if you take that same vector v, and I say first gradient, say plus twice the second one, I'll still get a 0, right? Because at the end, v times this guy is 0, v times the other guy is 0 as well. So v is orthogonal to any combination. You could write this way, basically. This times v will always be 0. Right? Okay. Sorry, let me write the v. Very good. Okay, fine. Then what does it tell me about my optimization problem? Here is the conclusion. Let's say I'm trying to optimize f. My goal, my objective function is f. I want to minimize f, x, and x is inside my intersection, right? And suppose the minimization happens at a particular point. Let's say it is fx star. In the picture, this x star, suppose, is like the optimal choice, okay? Then what does that mean? Anywhere I try to go around this, anywhere I try to jiggle, there is no way I could make this smaller than this guy. This is like the optimal, right? That means there is no jiggling that should be giving me a change, okay? For that to happen, your f gradient, now you're thinking about f. You forget about the defining equations. All you care about is your objective function, right? How do you change your objective function? Perturb it. Do your directional derivatives, whatnot. Try to get better. It better here means if I'm minimizing, smaller. And if you're at the optimum place, by definition, you cannot get better. That's like the optimum place. How could that be? That means all your directional derivatives, they are not going to work at all. And what does that mean? Your guy, take an inner product with any direction, should give you 0. In other words, it should be orthogonal to all the directions you could consider. In other words, it should be orthogonal to all the tangent vectors. You know, in other words, you should be able to write this guy as follows. It should be written as something times the first one, something times the second one. Let me write this a little better. Then I have a better written version below. I will read it to you as well. So a necessary condition for optimality is your gradient at that point should be satisfying this type of relationship. The gradient of your objective should be given as a combination of gradients of your defining equations. This is the only way you will get all the tangent directions giving you 0. Okay? Otherwise, you should be able to find the direction to jiggle that way, make it smaller. Okay? And this is called the first necessary condition for optimality. So let me show you the more official version. Where did I write it? Yeah, right here. First order necessary condition for optimality. If it is a local minima, I'll define what's the minimum more precisely in a sec. But intuitively, we all know what's a minimum is, right? And so to be able to have a minimum, you have to satisfy this relationship, okay? And now, if your equations are simple enough, you can just try to solve this as well. Let's say your f is something not so complicated. Let's say this is my f. What would be the gradient? Let me write it down. Take derivative with respect to two variables, right? Not too complicated. Oh, that wasn't fun. Okay, I think I'll try to do it later. Okay, so the gradient here will be this. You guys can help me. So what is the derivative with respect to x1? Looks like 2x1 and x2, 2. Is this correct? Yeah. And then the equation here, I only have one equation. h1x turns out to be 3x plus 2x2 minus 5, right? This has got to be 0. What's the gradient of this? 3, 2. Right? Now, what do you know? This gradient has to be a multiple of this guy. So now you know delta fx, which is 2x1, 2, is some number 3, 2. Right? So what do you know now? 2 is 2 times lambda. Lambda should be 1. 2x1 should be 3 times 1. That means your x1 is 3 over 2. You already know the first coordinate of your optimal point right away. Okay. Then you will do a little bit more messing with it. You will figure out the second coordinate. You're done. Okay. So this looked like pretty abstract reasoning, but you have immediate consequences. So that's what I'm trying to say. To have any optimality at all, you have to take the gradients and they have to satisfy this relationship. This is not sufficient. It's necessary. Okay. It doesn't mean that you check, you found the point that satisfies this, it's going to be your optimal. No, because there could be more than one point satisfying this. They all satisfy the necessary condition. Then you will see which of those is actually sufficient to be optimal. Okay. The necessary is not doesn't mean sufficient. Yeah, exactly. Okay. So this is first order optimality condition. Let me wait. People are taking notes. And meanwhile, maybe. There was only one. So in the example I was doing, there was 2 sheets intersecting. Yeah, I'm talking about only one sheet at all. That's about it. Sometimes you have 1, sometimes you have 10. Depends on what you're working on. Sometimes, for example, you only work on the sphere, right? You want a unit norm vector, norm 1, satisfying a property. Then you have that equation, x1 squared plus x2 squared, xn squared equals 1. That's a very common situation. Okay. All right. Okay. Now let me introduce optimization properly. So optimization literature talks about 2 types of problems: unconstrained optimization, constrained optimization. What does unconstrained mean? The domain you're optimizing over doesn't have like a strict boundary. It's like an open place. That's what it means. Constraint means you have a closed domain you're optimizing over. Okay. Your domain might be this emoji face. You're trying to find the best spot. Okay. So open, unconstrained, constraint, close. And the formal definition of minima is this. You distinguish between local and global minima. Local minima is the following. You found a dot x naught, and then around it, you look at the points that are close to it. Let's say you pick an epsilon, you look at it around the ball, and all these points is going to give you something bigger. So locally, this guy is the minimum. It may not be globally the best, but at least in that neighborhood, that's your best shot. That's a local minima. And If it is like strictly smaller than everybody, then you will call it a strict local minima. In machine learning applications, you start optimizing, and quite often you will find one of those local minima, and that's what you go with. You don't know actually if it was actually the global minimum, like the best thing you could come up with. Your algorithm gets stuck in a local minima, that's what you are output. In some cases, we know there is only global local equality. We will talk about those cases, but that's rare in applications. All right. So now this was the first order. We also have a second order necessary condition. Let me introduce that guy to you. Here is the second order necessary condition. If this function has a local minimum at a point, and let's say that point is in your domain H, then you look at every direction in the tangent space of your domain, all these velocity vectors. When you look at the second derivative of your function, this is going to be like a Hessian matrix. And you put those tangent vectors from left and right, you should always get a number that is 0 or bigger. If you get a negative number, this will give you a way to get smaller. Okay. So second order necessary condition is this matrix should behave like a positive matrix, what we call positive semi-definite early on in the semester, right? PST. We look at the eigenvalues when they're all 0 or positive, we call it a PST matrix. So this is why this thing is behaving locally around this point. And why something like this happens? It's actually easy to reason from Taylor. You do your Taylor expansion. I'm trying to perturb my point in this direction V. And I'm trying to see if I can make it smaller. When you do your Taylor, you see this. And our first order condition already says this part should be 0, right? My gradient should be orthogonal to all the tangents. If this is 0, what you're left with is only the first and the second order term. And what I'm trying to do is like, I'm trying to check if there's any V which makes this left smaller than this guy. If this is local min, this is the smallest. Well, the left is local min plus here. If this is the smallest, that means everything here should be a positive number, right? So that's basically why this guy behaves like a positive number, and that's the condition. And as you see, Taylor gives you almost everything you need in optimism, right? So these are the two conditions of optimality. So if the first one didn't do the trick for you fully, you can go for the second one. Okay. And I'll leave this as an exercise. Like I was gonna say, write this function and try to write the second order condition. It's gonna take a couple of minutes, not much, but it's good to do it by hand once so that you see. Here, my domain will be just a sphere, and the function will be take a matrix multiplied with x plus u, and x from here as well, and see how are you gonna minimize or maximize this function. This will give you another perspective on this eigenvalues, so it's useful. All right, so far so good. Okay, now the next thing that is important and useful is the notion of convexity. What is convexity? So let me first define a convex set. A convex set means the following. Take 2 points in that set, and then draw a line segment between them. That line segment has got to stay inside your shape. So let me draw some pictures for you. Let's say this is my 2 points, and I draw the line segment. It got out of the shape. That means it's not convex. This is not convex. But as you see here, any 2 points you put in, the line segment stays inside, so it's a convex set. And the line segment, if you're going to write it algebraically, is written this way. Your first point times a number between 0 and 1. Your second point times 1 minus that number. If you think about all these, this gives you the entire line segment. When lambda is 1, you're at here, x. When lambda goes to 0, you end up getting at y. So the entire thing gives you the line segment. Why do we care about convexity? There are many reasons for this. Let's say you see an optimization problem. It looks complicated. You don't know if it is hard or easy. Some optimization problems look rather complicated, but when you call a software, it just does the trick very quickly. Okay. And people are trying to understand, what kind of problems are hard, what kind of problems are easy. Yeah. One thing that humanity managed so far is like, if your problem is expressed in terms of convex sets and convex functions, which we will define momentarily, then we have a hope that it might be an easy problem. Okay. And convex stuff became like a laboratory for developing more ideas. If you have an idea that doesn't work for convex functions, forget about it. Okay? So it should be working well for convex stuff, then you hope it can also work in the wild somewhat reasonably. Okay? So for example, in machine learning, what do? We regularize, right? So we take this objective function and we add to it L1, L2. We add something to make that objective regular. And what is not said, but intuitively what people are thinking is like when you regularize, the objective starts looking more and more like a convex function because norms are convex. You're adding something convex, pushing it in that direction. So when it becomes like a convex, you have an idea how it is going to behave. Okay. So that's so far what we managed. It's not the end of the story. We still don't know how to distinguish between easy and hard problems systematically. Humankind is working on it. All right. So convex function. So this is a convex set. What's a convex function? So a convex function, suppose it's a function from many variables to one variable, Rn to R, or it could be from a convex set inside Rn to R. That's a function. And this EPF is what's called epigraph of your function. What does that mean? Look at all the values where the t at the last coordinate is just a number that is bigger than your fx. So let me draw a picture to make it more clear. Let's say my f is what I just draw here. So if you take any x, here's its fx, right? Now, if you think about all the values bigger than that, you get everything above. Now draw all that stuff. And the shape you are getting should be a convex shape. Then you call it a convex function. Okay? Tell me, Adam, what's going? Very good question. So Adam is asking me, why these convex functions are looking so nice. So let me try to pull up some pictures. For example, this is a typical convex function. Okay. And the reason you would expect this kind of shape is like convexity, which we will see soon, is again related to this first and second order type conditions. And the second order condition is the Hessian matrix being PSD. And when you get a PSD guy, it usually gives you a shape of this sort. So locally, this is how convex stuff will always look like. Because this is the minimum, When it's convex, we know there's like a one global minimum. That's why we like it. But if the shape would be going up and down, that's more complicated. Okay. Okay, let me get back to what I was talking about. Okay, so this is a convex function. And there is an equivalent way of the same definition, which I personally find more intuitive. An equivalent way of talking about the exact same thing is this. Let's say I took an x here, this is fx, and I took a y, which is here is fy, and I draw a line segment between them. The line segment stays above your graph. Okay, that's an equivalent way to think about convexity. So pick the way you like, right? I'm going to give you a couple more ways. So this is more mathematically, you can write it this way. So this is the line segment, fx, fy, they are getting combined. And it always stays above the value that function was created. Okay. So the thing, let's pick one example, let's say half. Okay, so I'm saying this is true for every lambda you could plug in. For now, let's say you plugged in half. So you're right here. So the thing on top is fx plus y over 2. The thing on top is what you see in the left, right? Right here. And the thing above is whatever is on the line, which is fx plus fy divided by 2. Okay, so the thing on the line is always above the thing on the function. The thing on the line is right-hand side. If this is half, fx divided by half, fy divided by half, sum it up, this is what you'll get. And here, f inside x plus y over 2, this is what you would get. And the left being less than the right means the thing you get from the function is always below what you get from the line segment. Okay, that's an equivalent way to think about convexity. And there is one more way, which is this. If you are at a point x, and if you want to go in the direction of a point y, you take that direction, y minus x, you multiply it with the gradient. That always stays below your function. So what does this mean? How does it look? So let's say, let me try to plot a random convex function. Okay, this is my convex function. And then I am at that point fx. Here's my point y, right? I'm going to take the gradient direction. And I'm going to go in that direction this much. So like here. And that will be always below what the function was giving for y. So this is fx plus. Okay. So the slope fixed gone in that direction always goes below your function. That's what convex means. Right. All right. And there's also a second order condition. So in the one variable world of calculus, if you remember many years ago, probably they told you the convex function is like take the derivative twice. Second derivative is going to be a positive number. Right. And in the multivariate world, what does that mean? Take the derivative twice. You will get a matrix now and plug into that matrix from left and right all the tangent directions. You should always get a non-negative number. That's convexity. If you get always positive, it's even better. You call it strictly convex. That type of functions behave much nicer. For example, L2 norm, standard Euclidean norm, is strictly convex. So that's why when you regularize something with L2, it starts behaving much nicer. Like it becomes closer to behaving like convex, essentially. All right. Okay, so far so good. Very good. Let me see if I want to say all this stuff to you or not. Yeah. Exactly. So this, okay, give me 1 sec. All right. So in optimization, people will sometimes talk about domains like this. Let's say this entire shape is where are you optimizing? And they'll talk about constraints. So the constraints for them usually would be like this direction is first constraint. This is my second constraint. This is my third constraint. This is my fourth. This is my fifth. Okay. So for example, you say, if I take dot product with this vector, I should be at least 5. So you got to be bigger than here, right? And with this vector, at least 3. So this is how linear programming from this war times came about. So I should put at least this much somewhere. You put all your constraints, then you try to optimize. Okay. Then when they talk about it, just to give you the language, when they say constraints, they usually mean only the boundary. The stuff inside, they will call it the interior. Okay. When they mean active constraints, it usually means you're talking about stuff on the boundary. For example, if you're here, the active constraint is only this guy. If you're at this dot, now you have 2 active constraints. Both of them are active on this particular corner. Okay. And if you're inside, usually you think like I'm not talking to any constraints. I'm like inside feasible region. Okay. So it's called interior. And let's see, do I need to tell you anything else? For example, interior of this curve is just this little dots on the curve, nothing more than that. The curve doesn't have like a 2D interior. It just has a 1D interior. I think that's enough. So affine and convex hull, we don't necessarily need it. If you see it somewhere, it's in your recording and the lecture notes are getting uploaded. You can always read it from here. What we need to know is what is written here. Let me read it through. You have some closed and convex domain you are trying to optimize. And the function you are trying to optimize is also convex. Then if you solve the local problem, congratulations, you also solved the global problem. For convex stuff, local and global minimum is the same. That's why they are nice and easy, okay? This doesn't mean that global or local minimum is unique. It's only one point. It could be a collection of points that are all minimum, okay? But there is only one global minimum number. Let's say they all are making your objective function 10, and that's the smallest you could achieve. That's it. If you found one of them, you're done, okay? That's why structurally convex stuff is much nicer. As soon as you arrive to local minima, you know you're done. Okay, and if your function is concave, which means it's like minus a convex function, and you do the same story with the maxima instead of minima. You know, imagine flipping that graph we were talking about. Your convex function, flip it over. Now it becomes concave. Then you have a unique max instead of min. Okay. But if you start combining convex and concave to each other, then things get much more complicated. You know, it almost feels like I can handle convex, I can handle concave. Let me take a convex guy, add it to a concave one. Let's see what I got. It gets surprisingly a big family all of a sudden. Okay. All right. So far so good. And I was saying, you know, why for a convex function, this type of super nice behavior happens. Let's try to understand. Suppose we don't know the fact, and we are thinking maybe there is a local minima here and there's a global minima elsewhere. Okay. And let's take the line segment between them and maybe even take the middle dot. And what I'm assuming is like the second guy is a global min. So x star star is say less than fx, okay? And what I told you is like something like this cannot happen. Local and global are the same. Suppose that happens and we will try to get to a contradiction to understand that's not gonna happen, okay? Suppose this is a local min and there's another one. It's again a local min, but it happens to be even smaller, say, for a second, okay? Let me take the line segment between them and even take like the middle point in the middle, okay? And now let's write this definition of convexity. The function at the middle point is less than equal to half times the first, half times the second, right? This is correct. And then I know this guy is less than this. So their average is for sure less than my point. Let me make it go left. So I already figured this thing in the middle is smaller than my local minima. Well, you can keep taking stuff in the middle. Now you'll go there. You'll go there, okay. You'll eventually arrive to the neighborhood of this guy, and you would know stuff in the neighborhood is smaller than that, which contradicts the definition of local minima, right? Locally, that should be the best shot. So what does that mean is like nothing changes actually on this line segment, okay? This minima and this minima, they all give you the same F output. So everything on this line segment will be a minima. Okay. So for convex stuff, local, global, all the same. Something like this never happens. Yeah. All right. So that's intuitive reason for why this is happening. Actually, it's almost a proof. You write this down more carefully, that becomes your proof. We don't need to do that. All right. Okay, very good. Now, what is the consequence? We have two consequences for this. One is how do I find the local min if I am unrestricted? So in the restricted constraint case, the gradient should be a multiple of the gradient giving me that sheet, right? If I have no restrictions at all, I'm allowed to pick any number. Then there is no gradient to multiply with. So in that case, your gradient should be just literally 0, okay? If you're in an unconstrained case. So I see I confuse you, so let me write. So what I'm saying is this. This is your entire domain. And when we had a function defining h1 equals 0, we were taking its gradient, right? And we were saying my local thingy should be a multiple of that gradient, right? That's what we were saying. Now I don't have any h at all, so this gradient is going to become 0. So any lambda times 0 will be 0. So if you don't have any constraints, local minimum is the same thing as, or at least necessary condition, is like take the gradient, it's got to be literally 0 if you don't have any constraints at all. It gets much more easier than the constraint situation. And that means if you're trying to do convex without any boundary, just take the gradient, find the point that gives it to a 0. You found your local minimum. Since local is global, you also found your local minimum, you're done. Okay. So if you're in that situation, that's the nicest case. Just compute the gradients, solve them, done. Okay. But of course, we are assuming this function f is convex and also differentiable. I am able to take that gradient. That's what I'm assuming implicitly. There are convex functions that are not differentiable, but we can still optimize them. We will talk about them later. For example, standard situation in machine learning, you will have what's called empirical risk minimization, right? Sum up your loss on all the data points, take the average. That's what you're trying to minimize. That's what we do all the time. Quite often that becomes like a convex but not differentiable situation, which we can use some of the stuff we will talk about later. Okay, very good. So this is the first consequence, which is making your life pretty easy. As soon as you get a convex function without any boundary, look at the gradient done. And if you have even more, there's a small amendment to this. If your function is not only convex, but strictly convex, which means all the inequalities we talked about are strict. We were writing, fx plus y lambda blah blah less than equal to something. That's going to be a strict thing. Or we had this gradient version, right? Gradient is always less than equal to, it's going to be always less. That's strict convexity. In that case, there is only one single minimizer or maximizer. It's not like a collection of local min, it's just literally just one thing. That's even nicer. Okay, so now let's do an example. Okay, I talked too much. A pause for me, a couple of minutes is good. So here's something that you will see all the time, all right? My domain is x1 plus x2 plus xn. They're all equal to sum into 1. And they're all non-negative numbers. Basically, this is like a probability situation, right? So x1 represents probability of the first class, say x2 second class, etc. Think about it that way. All possible probabilities you could create. And this function is called the entropy function. Right here, as you see the definition. Now the question is, what's the maximum entropy situation? Let's maybe try to think about it first intuitively. I got like, say, 10 options, okay? And then I'm going to assign probabilities to my options. And entropy should be some notion of randomness. What situation is like the most random? So intuitively, you expect they should be all looking the same. I have no idea what to do, right? So all of them should be 1 over 10, 1 over 10, 1 over 10. Or in this situation, 1 over n, 1 over n, 1 over. That is supposed to be like the maximum entropy because that gives me no information whatsoever. Okay? So if this entropy definition is correct, that should be the case, right? So now let's check, okay? So try to maximize this function on this domain and see what you can reason about it. I'll give you a couple of minutes. Yeah, of course, we will use the tools that we have been driving. So take the gradient, take the second derivative, see how it looks. Is it convex or concave? Since it is maximizer, you expect it to be concave, right? So convex was giving you min, concave was giving you max. So the thing should work out as like, I take the derivatives, I see this is a concave guy, so there's like a unique, like nice maximum, and I'm gonna go find it. Okay. Think about it a couple of minutes, then we will do it together. But it's good if you work on it a little bit. I hope the problem makes sense. We are trying to find what is the maximum entropy configuration. Well, of course, I don't know the answer. Even if I would know, I would forget in 5 minutes. So I'm doing it at the same time with you. Fair is fair. So you know, for now, you can forget about like the boundary and stuff. Just think about your like an interior point. Everything is positive and nice. Now, see how things look like there. No, or you can use the boundary to it's up to you. Yeah. Mhm. That's a good idea too. So the H, so for that, you need to use this guy as the defining function H. So if it is confusing, you call this F, this is our objective. called that guy h and take its gradient. That's also a good idea. Yeah, x1 plus x2 plus xn equals 1. Or minus 1 equals 0. Take the derivative of it, compute the gradient of that guy, and see what you got. And if you have an eye on art, if you are somebody who enjoys art, you can always attach optimization to art. It's an ancient Greek idea that the nature somehow picks the optimal shapes. Let's say a soap bubble is like a sphere because that's like the optimizing shape for energy. Anytime you do optimization, you can also attach it to your artistic or evolutionary ideas. All right. Okay. So let me try to walk you through this and end your pain. Okay. So I see there like xi times logarithm of xi type stuff. I kind of don't know what to do with it. So I said t ln t, when I take derivative, what happens? Let me check. I take the derivative of the first one, t derivative 1. So I got the second one here. Then first one times the derivative of the second one. I got like ln t plus 1 as a derivative. So it means when I go write the gradient of this guy, I'm going to go take derivative of the whole thing with respect to the first variable. And the only thing inside that deals with the first variable is like x1 times ln x1. Right. So the first thing is going to come out like this. Like that. Okay. And there's a minus I forgot, so I put it later. So there's a minus in front of everything. Okay. And now you're going to take the second derivative to get the Hessian matrix. I got the second derivative, which means I'm taking one more derivative here. Derivative of 1 is 0. Derivative of ln is 1 over t. And there was a minus I forgot, so I'll get like minus 1 over something. That's how the Hessian is going to look like. Okay. And as you see, this is a clearly negative definite function. Everything is 0 except the diagonal, and everything in diagonal is negative. Okay. So this guy is clearly like a negative matrix, right? And as soon as none of this stuff is 0, if it is 0, you got to be careful. There is no 1 over 0. Actually, when I first moved to Texas, somebody told me, welcome to Texas. Here only Chuck Norris can divide by 0. And they told me some more jokes, which I'll not tell now. So this is clearly a negative matrix. It's like everywhere 0 except the diagonal, and everything on the diagonal is like a minus number. So what does it mean to have a matrix, the Hessian, which is always negative? That means your function is concave. Okay, if it is always positive, convex, always negative, concave. So that means H is concave. And actually, since this is always like strictly negative, it's actually not only concave, like strictly concave. And that means unique maximizer. Okay, that means this guy has only just one single maximizer on this domain. And that's the thing I need to find out. Okay, now here's a funny argument. Suppose I'm thinking about something like this. Let's say for only 3 variables, let me illustrate. Let's say I'm thinking about like probability 1 over 2, I don't know, 1/4, 1/4, right? This versus this two of them. Let's say my guy A here, my guy B. A or B, let's say, you plug it into that H function. You see you're going to get the same exact output, right? Because it's a very symmetric function. It takes like half times log half plus 1/4 times log that plus that. It doesn't really care how did I order them. 1/4, blah, right? So this 2 will give me the same exact output from this function, which means none of them could be the unique maximizer, right? Because they're giving the same output. Maximizer is unique. There's only one dot. So that means that dot, whatever it may be, is something I cannot change by moving things around. So how cannot you change something by moving coordinates around if all coordinates are the same? So that means, here it will be 1/3, 1/3, 1/3. So moving around will change nothing. And that's the unique maximizer. In general, it's 1/n, 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 1/n. Okay. So everybody should be treated equally. That's when you get maximum entropy. So only by knowing there's a unique maximizer, you immediately know what that is. Because as soon as you see two different coordinates, swap them. You get a new vector, which gives the same output from the function. If there is no two different coordinates, they're all the same. Okay. That's the maximum entropy situation. So fair dice, for example, is the maximum entropy. Every face has the same probability to get. But if it is not fair, say one face is more probable, then you know something about it. Okay, very good. So this is one specific case of this entropy. It is kind of a general principle advocated by a very prominent American statistician, Jaynes. It's called Jaynes maximum entropy principle. So if you're trying to model something, put everything you know about it, then let the rest be maximum entropy. That's basically Jaynes maximum entropy principle. And it became very successful in ecological models and many other things. So there is no proof of this. This is like a philosophy, more or less. So, put everything I know about my model. These are facts I know about this object. Put them in, then let the rest be just free probability. And among those all possible probability options, pick the one that is the maximum entropy for your model. That's Jaynes maximum entropy principle applied in ecology, statistical physics, you name it. Okay. So all over the place. And it also inspired maximum entropy optimization algorithms that are used all over the place. All right, so let's get going. What else I want to tell you? So here, we literally maximize the entropy. This is the entropy function. And we figured that's maximized when all coordinates are equal. Here our constraint was the coordinates sum up to 1 and they're all non-negative. Okay. So here we are thinking I just have a probability estimate on my classes. But if you're modeling some physical stuff, then you will put your constraints in the definition right here. Instead of this, you will have your physical constraints. Then after that, you think about, okay, this is all I know about it. The rest is probability. Everything is possible for the rest. And among those, pick the one that is maximum entropy. That's what's called Jaynes maximum entropy principle. As I said, this is not like mathematical proof, but it seems very good intuition. Yeah, okay, now let's see what else I want to tell you now. No. Should we do it now or next time? Let's see. I got 7-8 minutes. Yeah, let me get going with this part. Now we'll talk about a collection of algorithms called descent methods. What does it mean? I am at a certain point X. Try to find a vector V, where for any small number t, if I go in that direction, I'm becoming less in terms of objective function. So this is like a good direction if I'm trying to minimize, okay? That direction V is called a descent direction. And the collection of algorithms we are starting to talk about always tries to find a descent direction first. Let me find a good direction to get less in terms of objective, minimize, lessen the cost. And then the next question would be how much I should go in that direction. Okay. So first you need to find a descent direction. Second, what's a good number t to put in front of your direction and go in that way? Because locally it's a descent direction, but if I stretch it too much, maybe it stops being a descent, maybe I even start increasing. Okay. All right. So that's the main idea. Let's see how are we going to execute this. So first off, there's an easy characterization of all the descent directions. These are the guys, you take your gradient, multiplied with that direction, you get a negative number. Why? Because this means directional derivative in this direction, as we talked about. And directional derivative has got to be negative so that you're decreasing, right? This is just intuitive. So what I wrote there, maybe looks like the way I wrote is confusing. F transpose V is the same thing as F inner product V or dot product V. If you're thinking, how am I going to find the descent direction? You just need to find somebody that satisfies this relationship. When you dot with the gradient of your objective, it gives you a negative number. Okay. And now maybe let's think about it. Okay. I got a whole bunch of options. Which one is the best? There's a lot of descent directions now. All of them are fine. If I would be greedy, which would be like the best in the sense that, let's say I'm only talking about vectors which has unit norm 1 to normalize stuff. Which direction is the best in the sense that in which direction this is going to be the smallest? So you can think about it like this. Your gradient is a vector, right? Let's say this is that vector. Inner product is related to the angle. I'm trying to find a vector. When I look at the angle, I got the most negative one. So the intuition suggests it should be like, take the gradient, put it a minus. That's the greatest angle you could make, right? So if you work it out mathematically, that's what comes out, okay? So the best direction in terms of giving you the most bang for your buck is given by the gradient itself almost. You take the gradient, put a negative in front. And if you're looking for a unit norm, normalize it with its norm. This is steepest descent direction. Among the descent directions, this is like the best one with this perspective. But don't forget, with this perspective, we are only looking at first order information, right? We're only looking at like the first thing in the Taylor expansion. I'm only looking at the first directional derivative, okay? In terms of this is the best one. But maybe if I would also look at the second, I would find even a better direction. That's possible, okay? If you're only using first order information, only just first perturbation, that's the best you could do. Yeah. So this, we need to think about it from a computational perspective, of course. Mathematically, you can say, let me open the second, let me open the third. I'm going to get more and more information, and I'm going to find a better vector than this guy. Yes, mathematically, yes, but that's not what we want to do. We want to actually run it on our computer. So we need to think about how expensive is doing all this computation, right? Okay, so the first algorithm takes that best direction. You're at a point, say, xk. It should have been here, subscript, I'm sorry. Okay, I don't know why I wrote it this way. xk is your current location. I'm going to do an update to decrease my objective. What do? I go in the best direction, minus gradient. And I'm going to go this much. I don't know what's the best number to put here. That's called learning rate. We will talk about it, okay? So this is gradient descent algorithm. The whole algorithm is what I just wrote there. At every single step, compute the gradient, put a minus in front, go in that direction a little bit. How much you go, you'll have to think about it, okay? All right, so now, of course, two immediate questions. What should be that number I'm putting there, learning rate? Second, let's say I iterate this. How many steps is good? Like after I did 100 steps, do I know I'm closer to the optimal? Should I stop? How many steps do you expect until the algorithm converges to a local minimum? So two immediate questions. Okay. And I am almost at the end of my time. So how it is going to come out starting next lecture is we will be able to prove estimates on this number of steps. After how many steps you're confident that you achieved to close to an optimum. We'll be able to prove it for nice functions. As I said, if you're unable to prove your algorithm is working nicely for convex objective functions, forget about the rest, okay? So we'll prove some estimates for convex and differentiable and nice stuff. And that gives you an intuition on how you expect it to behave elsewhere. Okay. That's about it for today. Thank you so much.